In this video, we'll be covering the first part of the sixth module of EC304 VLSI. In the sixth module, we basically deal with the arithmetic circuits, the hardware implementation of arithmetic circuits like adders and multipliers. So in this particular video, which is the first part, we will be dealing with static adders and carry bypass adders as per the syllabus. But in order to understand the static adder and carry bypass adder, we will also be revising the half adder, full adder and dynamic adders, in which half adder and full adder have been already learned by us in the previous logic circuit design classes. So we'll start with the basic half adder. So half adder is the most basic of the adders that we have learned and are learning. So basically it has two inputs and two outputs. In this case we have taken A and B as the inputs and the sum and carry will be the outputs. And in case of the hardware implementation of arithmetic circuits, we are basically dealing more with bit additions, that is 2-bit additions or like bitwise additions. We will not be dealing with more of other range additions, but we'll be dealing more with bit additions. So this is a standard truth table of a half adder, in which we basically have two inputs, 0 and then the outputs are marked accordingly. So as we all know, but just to revise, I'll say again that when we add 0 and 0, we'll get sum as 0 and carry as 0. 0 and 1, sum 1, carry 0. 1, 0, again sum 1, carry 0. And when we have 1 and 1, we'll get sum 0 and carry 1. So that is how the truth table of a half adder is. So next we'll go to 4-bit addition. This is a serial chain of 1-bit additions. So what happens is the leftmost, in this case the rightmost bit is the LSB and the leftmost bit is the MSB. So when we add the LSB, first there is 0 bits like A0 and B0, we'll get sum as S0, and if there is a carry, it will be given to the next addition. That we'll add the carry of the LSBs with the next bit. That is A1 plus B1, and if there is a carry, that is added, and the sum is given as S1 and the carry is given forward, and this cycle repeats, and that's how we get the answer as a sum and carry. So this is what is displayed in this figure, that we have two inputs and if there is a carry, that is also added and we get the sum and carry. So next we'll go to the full adder. So the expression for the full adder is what is given here. So after writing the table and then reducing it using K-maps, which we have done in previous semesters, we get these expressions for sum and carry out in a full adder. The sum is A XOR B XOR C in, and the carry is having the expression AB plus AC in plus BC in. The same expression can be rewritten as AB plus C in A plus B, which is in the distributive law, and AB plus C in A XOR B. So next we'll move into this topic called carry delete, carry propagate and carry generate. These three words are really important to study the further adders. So what it basically is when we have the inputs A and B as 0, 0. So this is basically the truth table of a full adder. When we have the inputs as 0, 0, regardless of what the scene is, so either the scene can be 0 or 1, the output or the Cout comes out as, the carry output comes out as 0. So whatever the scene is, if A and B are 0, the carry out will be 0. And in the second case, if A and B are 0, 1 or 1, 0, the carry gets propagated. That is, if A and B are 0, 1 or 1, 0, then whatever it comes in the C in position is what comes out as the carry. and that is carry propagate, and then we have carry generate, that is if A and B are 1 1, then regardless of what scene is, the carry will be 1. So that is carry generate. So these are the three carry delete, carry propagate and carry generate. So from this truth table we can deduce that carry generate is AB, that is A, when A and B is 1, that is when carry generate is, that is G is equal to AB. Carry propagate is when A0 B1 or B0 A1, which is A XOR B, and carry delete is when both A and B are 0, that is carry delete is A bar B bar. So there is two methods in which we can reduce a function. So that is we can reduce the adders using logic functions and using circuit functions. So it is an easier method to express adders using generate and propagate. That is where we'll be using it in the further adders. So I just said that here. So CO, that is carry output, will be G plus PCI, that is generate function that we found out earlier, that is AB plus PCI. P is A XOR B CI. It will be equal to C0 of the carry out, and sum expressed in terms of generate and propagate will be P XOR CI. So we found out P and G so that we can write the sum and the carry out in terms of G and P. So next we move into the syllabus. So the first part of the syllabus, it says static adder. So don't get scared seeing such a big figure because it is a really simple thing. So static adder this is a circuit implementation of a static adder, CMOS implementation using 28 transistors. So static adder is a primitive adder implementation as it consists of a lot of transistors. To implement the static adder design, what we do is we simplify the expressions that we got for sum and carry, which makes it easier for us to restrict it to 28 transistors as well as draw it. So the sum expression, as we all know, is A XOR B XOR Cn, which in an expanded form when we write it, it will become AB Cn plus A B bar Cn plus A bar B Cn plus A bar B bar Cn. And the carry expression of C0 is AB plus ACI plus BCI, which can also be written as AB plus CI. When we take it out, we get A plus B. So since in CMOS implementation, we take the inverse and implement it, it is easier for us to find C0 and implement, C0 bar and implement. That is why we are taking C0 bar. C0 bar is carry out bar, which we'll get the expression for carry out bar by simplifying the expression of C0 bar and simplifying it using the different Boolean functions. So I don't think it will be necessary to explain each step one by one. It's only the Boolean laws that is being used here, and finally we come to the expression that C0 bar is A bar Ci, B bar Ci bar plus A bar B bar, and when we use C0 bar to find the sum expression, we will get it as ABCI plus C0 bar A plus B plus Ci. So using these two expressions, that is this one and this particular expression of C0 bar, we get to draw this diagram. So as we can see, the first part of this diagram, that is up to X, is the implementation of C0 bar, and the second part is using the C0 bar to find the sum. So as we all know, the expression for C0 bar is A bar Ci bar plus B bar Ci bar plus A bar B bar, and the expression for sum using C0 bar is ABCI plus CO bar plus A plus B plus CI. So I call C0, it is same as C out or the carry out. So I'll be explaining how this diagram is drawn. So as we all know, it is a CMOS structure. We'll have the NMOS part down and the PMOS part up. So as we know, C0 bar is A bar Ci bar plus B bar Ci bar plus A bar B bar. So this is A bar B bar plus A plus B into Ci. So it is same as ACI plus BCI. So the multiplication part is written like this and the addition part will be written like this. Which how to draw a CMOS circuit has been explained in the previous modules. That's why I'm not going into depth in that. And here again we can see the same thing like A bar B bar and then A plus B into CA bar. And then when we take the inversion of the same thing, we'll get C0 out here. And the next part is the sum part, and we know that the sum is equal to ABCI. That ABCI, or here we can see ABCI for the NMOS and ABCI for the PMOS, and we also have the other plus part which is C0 bar into A plus B plus Ci. And that's how the sum is got. And as we did for C0, we also do the inversion to get the sum. So that is basically static adder, which is a simple principle, but it becomes complicated in the hardware side because of the number of transistors. So that is why we have to look for alternate options. So one alternate option is the dynamic adder or the Manchester carry chain adder. It is implemented using what we learned earlier, the propagate and the generate functions. Basically, it has two modes, which is the pre-charge mode and the evaluate mode. We have the diagram right here. So we have two modes for this, which is the pre-charge and evaluate. In pre-charge mode, this phi value is equal to 0. So then C0 will become equal to VDD. That is like PMOS, when phi is equal to 0 gets turned on and becomes equal to VDD. So C0 bar will be equal to 0. So whenever it's in pre-charge mode, C0 bar will be equal to 0. Then we have the evaluate mode. That is when phi is equal to 1. So this part becomes equal to 0. And then in this part, when phi is equal to 1, there is this one condition that we have to always keep in mind when learning dynamic adder. The Pi and Gi cannot simultaneously become 1. So either the Pi is equal to 1 or the Gi is equal to 1. So in the evaluate mode, when phi is equal to 1 and Pi is equal to 1, then C0 is equal to Ci. C0 bar is equal to Ci bar or C0 is equal to Ci. And in the other case, when Gi is equal to 1 and Pi is equal to 0, then C0 is equal to 1. So this is the two stages in the dynamic adder. And then we have the 4-bit implementation of the same thing that we learned now, the carry chain adder. So this has the exact same thing, but it has 4 stages. So like for each bit, we do the same process and repeat the cycle as many bits as there is. So that is the 4-bit Manchester carry chain adder. So the total propagation delay for this structure is equal to 0.69 n into n plus 1 RC by 2, where n represents the number of bits. Like this is a 4-bit Manchester carry chain adder. So the n is equal to 4 and the R and C represents the respective parasitic capacitance and resistance. If this is, since all the PMOS and NMOS are made up of MOSFETs and which basically has resistance and capacitance, so it represents the respective parasitic capacitance and resistance. So the advantage of this over the static adder is that the number of transistors will be less. So now we'll go to adder optimization. So what we have seen till now is adder optimization using logic functions. Now we'll go into the adder optimization in the circuit level. That's where carry bypass adder and carry select adder comes into place. So we will start with ripple carry adder. So in this circuit, as we can see, what happens is there are 4 full adders. The first full adder we'll have the two inputs A0 and B0, which being the LSB bits, and the Cin comes and we get sum and carry. So the carry out of the first full adder will become the carry in for the second full adder, and which will be added with A1 and B1 to get sum S1 and C1 and so on. And finally in the MSB bit, the carry in will be the output carry of the previous adder, and we'll get this final sum and carry. So the problem with this ripple carry adder is that the carry ripples from one stage to another. That's why it gets its name. But due to this, we'll have a longer time delay. So the T of the adder is n-1 T carry plus T sum. That is the sum, the time taken for calculating the sum of only the final adder is, it depends, but it also depends on the time that each of these adders takes to find the output carry. So the total time taken for this calculation increases as the number of stages increases, and it becomes highly non-feasible as the number increases. So T carry is the time taken to generate carry, and T sum is the time taken for sum calculation. So the N affects only T carry and not T sum. That's what is most important here. That the number of bits affects only the carry part and not the sum part. So we have to reduce the dependency that the T carry that N has on T carry. So that's where we introduce carry bypass adder. Okay, so now we'll see the carry bypass adder. So in the carry bypass adder, what happens is that the carry is bypassed whenever the select line is 0. That is, the select line for this mux shown here is the propagate signals. That is, the select line is equal to P0, P1, P2 and P3. And whenever the select line signals is equal to 1, then C4 is equal to C0. And whenever it is 0, then C4 is equal to the carry generated from this part. So in that way, we can prevent this carry from rippling through the full adders, and it will save the time. So the time, it's really saved when we use it for the block carry skip adder. That is, in this case, we have a 16-bit adder and it is divided into 4 blocks. It is especially in this case that we save the time. So what really happens is the 16-bit is divided into 4 bits, and in each block, the same thing what we saw here is that. That is, if P1, P2, P3, P4, P0, P1, P2, P3 is equal to 1, then C4 is equal to C0, and otherwise C4 is equal to C4.